keep an eye on things, and we'll get that reset in just a second. So, all right. So I think I'll turn it over to Natalie to start the session.
Hi, good morning, everybody. So good to be here and meet a lot of new people and see some people that I've known. My name is Natalie Laudier. I am from NOAA NESDIS. I am the new commercial data program manager within NESDIS, and I've only been there a short time now. I was with the DoD and Navy and Army for about 20 years, so I'm excited to be here at NOAA, and first IROWG as well. So this is exciting group, and I'm looking forward to this panel of talks. So we'll go ahead and get started, and I'll introduce Christian Marquardt, and he is from EUMETSAT. So he's going to give the first presentation on radio occultation activities and status and future plans.
Thank you very much. It's a pleasure to be here. Thank you, Cliff, for your talk. Indeed, it was very inspiring. I'm a little bit worried because of some in the room know I have some hiccup, bad things with my foot, so I cannot even run away when you are now chasing me. So I better talk about what we do in Europe on future missions, and that will be indeed the first half of that talk. And then in the second half, I have a little bit more detailed technical stuff on things we have done, which are really coming from the reprocessing and which might be interesting for Romex as well. And we see how far I get and how far time comes. So, radio occultations. Our current operational mission is EPS, the EUMETSAT Polar System. That is 3 METOP satellites in total. METOP A was launched in 2006 and it was deorbited in 2021. All 3 of them carry the European RO instrument GRASS. METOP B was launched in 2012, is still and healthy, and will probably last until 2028, maybe a year longer. So people are discussing that to delay the deorbiting. And then there is METOP C, which was launched in 2018. We currently think it will live until the mid-30s or early 30s, we'll see. METOP B is drifting now since last year, so the local time is 9:20, not 9:30 anymore. They are all on the same polar orbit with the local time of 9:30 and at 820 kilometers height. METOP C has the problem that one of the gyros failed, so we are on the second on the replacement gyro. If that continues to work until the end of the lifetime, that's great. If not, it might end earlier. One of the problems with the GRASS instrument is that it's using legacy GPS code, in particular the encrypted codes for P1 and P2. And if the US Army will shut those frequencies down in the end of the 20s, and it will turn into a single frequency receiver. And that will not be so nice, of course. So then it's probably much less useful. The other mission that is currently operational is Sentinel-6, Michael Freilich. That is basically an altimetry mission at an orbit height around 1,300 kilometers. It carries a trick receiver from JPL, who kindly donated that to us. In late 2025, there will be the second Sentinel-6 satellite that will again carry an RO receiver. JPL is producing that data in near real time, but at EUMETSAT we are doing a non-time critical processing, we call it, for validation purposes, for climate purposes, and just to have another alternative. The RO instrument on Sentinel-6C, which is coming in 2030 probably, that hasn't been decided upon yet. So please, Tom, give us another receiver for that instrument. That would be very nice. There are some enhancements on that platform. Being a trick receiver like the ones on Cosmic, it is currently taking observations from GPS and GLONASS, and the update to Galileo is in place. It has been tested on Cosmic too, so I assume we will hear something about that in the conference. On Sentinel-6, it will come hopefully at the end of 2024, already on Sentinel-A, and we are going to extend the measurement range to up to at least 500 kilometers on Sentinel-6B, at least to see if it works, and I'm pretty sure it will. Then the big thing and the follow-on for the EPS is EPS second generation. EPS second generation is 3 pairs of satellites. We have always 2 flying in parallel, again on the METOP orbit, so 930, 820 or so kilometers high. They are on the opposite side of the orbit all the time. All 6 satellites will carry a GRASS-2 instrument, so that's an evolution from GRASS. The first one SGA-1 is scheduled for late 25 as well. And Sentinel-6B will follow 9 months or 12 months around that time later. And then the next pairs of satellites currently are scheduled for 2032 and 33, as well as 39 and 2040. So that's one of the particular things about EUMETSAT. For the big satellites, we have what we call programs like EPS or EPS-SG, and they run for decades. They are not one-off science missions, right? So RO is flown on both. An interesting part for the first satellite, it will fly in tandem with METOP-C for up to half a year shortly after the launch. So we have for the first time the opportunity to directly compare the same occultations because they are flying something like 20 seconds behind each other. For Cosmic 2, something was done initially when the satellites were close together. We have a chance to do that here. What is the difference? So this is a picture of the receiver. So they are all built now and ready. For those who know similar pictures from GRASS, the antennas have been much simplified. The box in the middle looks the same. There are still low noise amplifiers as RF front ends. One of the particular features is that during the design, there was a lot of concern about DME TACAN interference in the L5 band because we are just measuring L5 in addition to the L1, so no L2 measurements anymore. There was a lot of concern about DME TACAN interference, so there is an active mitigation in the L5 bands for that, and we will see if we need that or not. It's taking measurements for GPS and Beidou at 200 Hertz over the entire vertical range and at 250 Hertz for Galileo. There is no GLONASS because GLONASS hasn't been modernized to code division multiplex signals, so we don't take them. The vertical coverage will be from, as GRASS, basically from -300 kilometers SLTA up to at least 500. And very soon after the launch, we will see if we can go a little bit higher up to 600 to cover somewhat more of the ionosphere. And it will have ionospheric products. That's also a new one. We have some ionospheric stuff now from GRASS, but only up to 300 kilometers. So we are missing the F layer very often. It has a proper open loop, so there's no code tracking required anymore. But if there is code tracking, it is used for the steering of the correlators in the system. And there is a difference to the American way that you did by going towards high gain antennas, you know, electronic beam steering and things. You don't increase the gain that much. There is a little bit higher gain, but that's really not the main focus. Oh, sorry. Is that better? Thank you. The main change is that we are moving to 10 correlators rather than just using one in the open loop phase. And the reason for that is, so I don't have a pointer, I think. But this picture shows a simulated signal on the left for the L1 frequency and on the right for the L5 frequency for a rising occultation. And what happens is that the Doppler and range models that need to catch the signal in the low troposphere, if they are a little bit off, then they will not find the signal on the main correlator. That is where the Doppler model points. So on the right thing, in the second figure, you see essentially power spectrum spread out over the 10 correlators. And you see that in the beginning, the signal can be slightly off. What we do then is in the reprocessing on the ground is to recombine the 10 correlators to a single time series of what the signal should be. In the third figure, you see a time series of the SNRs for, in blue, for the central correlator, and you see it is missing a lot of the signal. If we have the 10 in there and we combine it properly, then you regain it. And we think that the tracking in the troposphere is not necessarily improved by just raising the gain, but you have to do something in the open loop to track the variations in the signal that are off from your Doppler model. And I think, I mean, we had this discussion a lot. Why is Bayer working so good despite having low SNRs? I think they have much better Doppler models and range models in their receivers than we do. So the next mission that might come up is EPS Aeolus. That's the Doppler wind LiDAR in particular, but it's now clear that it will also carry an RO mission if it flies. The launch would be in the early to mid 2030s. It will have very likely also a GRASS-2 payload. As things are, prices went up, schedules went delayed. So currently that mission hasn't been approved by the member states yet, and it's not clear if it will fly, but if it does, and we all hope it will, then there will be another RO mission. So that's in short the outlook for EUMETSAT things. I'm coming a little bit to the technical stuff, and that is something that happened with the GRASS instrument on METOP-A in August of 2019. The figures you see are distributions of the SNR over time. And you see that on average, we are looking around 750 volts over volts. And then, of course, there is a distribution from the individual occultations. The first two rows are rising and setting occultations from MO1, that is METOP-B. And the second two rows are the same for METOP-A for setting and rising. On METOP-A, there was an outage for a few days around 1st of August. And then when we looked at that afterwards, then well, the setting occultations went on as normal, but in the rising one, suddenly, really within probably hours, the SNR dropped quite significantly. And because the satellite by now has been deorbited and we can't climb up to see what has happened, what we believe is that one of the feeders of the L1 signals has been somehow damaged, maybe by a small meteorite or something, because from the data analysis we did, we see that it's essentially affecting L1 CA signals, but not the L2. The L2 is affected because of the coldness tracking, but the SNR values is essentially affected as the L1 CI, and that is what you are seeing. Yeah. Oh yeah, sorry, I tried. What did we saw? Well, the antenna on GRASS is relatively complicated. I have a picture on that one. If a few of the antenna patches go out, then it means that the antenna reference center is changing, and that would mean that we are mismodeling it if you're not taking that into account, and that would mean that we are getting a bias. In the lower right corner, you see the biases with the thin lines between rising and setting occultations, and for METOP-A rising, there is indeed a split up between them after the event. So what we thought then is, okay, well, for the reprocess, and this is about 1%, that's 60 kilometers maybe. So it's not that bad for NWP applications, but Stig Syndergaard from the ROMSOF told us immediately for climate that is a no-no, we have to fix it. So what we're trying to do is we are trying to estimate the change in the antenna phase center that we would have to correct for. So we looked into things a little bit. At some point, RUAC, the instrument provider, told us that they think that the antenna pattern actually changed in a way that is direction dependent, and that is true. Again, in the lower left, you see a horizontal distribution of the SNRs, and for the rising antennas, there are two drops for viewing directions around 25 degrees azimuth away from the antenna borehole, in addition to the total one. And what we do think, so now there is a picture of the antennas, we do think that the upper two patches in the middle went out for L1, whereas the other changed. Because the complete antenna pattern is built by the superposition of the individual patches, that means the gain pattern is changed. And that also means potentially that the antenna location, the reference point changed in a way that it depends on the azimuth. So we tried to find out how that affects the biases. And it's the same set-off. The two colors are the two different satellites. And when you go to the rising occultations of METOP-A after the event, lower right, then you do see that suddenly we have a nice meridional pattern in the order of 1 or 2%. Is that right? Yeah, 1 or 2% plus minus in the biases that we see. So that's significant. I was not sure. Oh, thank you. So I'm not sure if he knew that biases can be azimuth dependent. And of course, that's also true for the random errors. This is standard deviations, again, from GRASS, the different colors at different azimuth angles, going out up to 60 to 65 degrees, where we now have very few occultations. That is why the noise is very noisy. But you see that if you're getting outer on the fringes of the antenna, errors are getting larger. There are probably multiple reasons for that. SNRs are lower at the edges of the antenna patterns. The sideways looking occultations have a lower descent rate, which is increasing the error. They are also traveling more through the horizontal distance, so we have a bigger impact of horizontal gradients in the atmosphere that will increase it. So it's complicated, and we don't know exactly how we can attribute that. So we are still trying to figure that out. But I thought it's interesting to see that it happens. And I'm also wondering, when we are thinking about modeling errors in radio occultations, if this isn't something we should take into account. Another thing we have recently done is reprocessing of cosmic 2 data. We do reprocessing of many missions. I've listed them there on the top. We wanted to do Cosmic 2 a little bit later, but because we had some discussions in the context of ROMEX about potential biases in Cosmic 2 data in, say, mid-latitudes, around 30 to 40 degrees latitude, We looked into that a little bit earlier. This is very preliminary data. If you look at the top right, so first of all, these are standard deviations as function of altitude. The green one is our reference that is coming from GRASS, and we know that at high altitudes, GRASS is very noise-free. Cosmic is a little bit better. The black line is the Cosmic 2 data as we got it from EUCA for ROMEX, and the red line is the data we get when we are doing the reprocessing right now. And we see that we have improved a little bit on the standard deviations. We think this is mostly coming from the GLONASS occultations. We are using 1 second clocks, which is improving the noise levels of those, so probably that explains it. Otherwise, on the top, you see the mid-latitudes, and I made a mistake. That is actually 30 to 60 degrees north. So for cosmic, it's going up to 40, 42 degrees, I think. And the lower picture will always be in the tropics. One interesting thing is, and we have been struggling with that for a while. Right now, we are producing about 15% fewer cosmic occultations than EUCA does. And that is because we are throwing out more profiles in our quality control. And I come to that in a moment. So on the biases, within ROMEX, some people, Neil, for example, showed that in, say, subtropical regions, a little bit farther northward and southward, there are large biases in the Cosmic 2 data that do not seem to appear in other RO missions. And here is an example of that. So in the top, that is the bias. Again, there is GRASS, which is somewhat negative. There is the EUCA data. And in the mid-latitudes, you see that there is this bulb of positive biases between, say, well, around 15 to 20 kilometers. And it's big for RO. And the other RO missions, when we do a similar statistics against the ECMWF forecast, doesn't show that. In the lower one, in the tropics, you see that the biases from the different processings and from GRASS align much more. If you look closely, you will find that around 20 kilometers, there is a little notch in the EUCA retrievals. 20 kilometers is where, as far as we know, EUCA is blending the wave optics below and the geometrical optics above. So that might come into role. But anyway, so we have this strange biases. Axel von Engelen, who really did most of that work, I should say that, remembered that Bill Schreiner at the IROC in 2018 in Denmark argued that you have to double difference the ECMWF data and to take out the influence of the background because of the different locations, because that might give you systematic impacts on the biases. And so we tried to find out whether that's true. So this is the bias against ECMWF. This is the direct bias if Cosmic 2 retrievals versus the GRASS profiles when they are within 300 kilometers and 300 hours. 300 hours, 3 hours, of course. So on the top again, that's the mid-latitudes. And you see that both the EUMETSAT retrieval and the EUCA retrieval have this, now it turns out with a negative sign, this negative bulb against the GRASS data around 15 to 20 kilometers, well, center is at 15 kilometers or so. For some reason, whereas in the tropics, they are both negatively biased against GRASS, but they are again much closer together. They are not completely identical, but at least they are closer together. So can one of these bulbs there, can that be explained by the background, which was Bill's idea? So Axel went on and he compared the ECMWF profiles that we extracted from the geolocations of the cosmic data and the GRASS data and just looked at the difference between them. And if you're looking in the mid-latitudes, there is this bulb again. And I try to go back and forth, and it's probably not working well. But if you want to believe me, that bulb is actually quite consistent with the direct bias that we see between the EUMETSAT processed cosmic data and GRASS. So we think that Bill's explanation works actually quite well for the EUMETSAT processed data. So why is that bulb larger for the EUCA processed data? And I mentioned that we are doing 15% fewer occultations from cosmic due to our QC. So we are throwing out more data. If we compare the direct comparison, if we restrict the direct comparison between GRASS and cosmic to the ones that pass EUMETSAT's quality control, you're ending up with bias structure which are looking very similar, like the Cosmic 2 EUMETSAT version against GRASS. So what we suspect is that the profiles that we are QCing out contribute to this additional bias in the UCA processing, which has more data. So it might be a QC thing. We don't know what it is precisely because we didn't have time to look into that in detail. From my experience, one of the problems with the American receivers is that the L2 tracking is notoriously bad. Sorry for saying that. And that is why it often ends above 20 kilometers. We have a QC, I say it, we have a QC that we are rejecting profiles when the L2 doesn't go deep enough. And the reason for that is that several years ago, we had a long discussion with the ROMSAF who said that extrapolating the data from higher up is giving them problems with biases and things in calculating reflectivity. Maybe that is part, but right now this is speculation because our analysis hasn't come that far yet. But I thought it's an interesting point to share. Right, last slide. We continue to operate on our future missions so that I don't have to run too fast, Cliff, I hope. We had this SNR analysis job and we saw that there are azimuth-dependent biases and standard deviations that we think might be important to include in error modeling. And we are trying to sort it out for METOP-A, so that's the reprocessed data set we are going to do will not suffer too much. I showed some initial results from the Cosmic 2 reprocessing. I would like to say that we are doing other things, commercial RO. There is a talk about that from us tomorrow. We are looking into RFI. There is a talk about that from Maria also tomorrow. And we talk about Romex also tomorrow. Thank you very much.
Thank you, Christian. Do we have time for questions? I'm not sure that we do.
Question. Yeah, I'm totally confused about all these biases, and I've been looking at it for 6 months. I'm totally confused. The next to your last slide, what is the? It looks like negative biases, but we're getting positive biases, and so what is that with respect to exactly? Cosmic minus glass. Okay, thank you.
We have time for one more question.
Just to clarify, what you mean by azimuth angle, do you mean off bore side or
Yes.
really off bore side?
Yeah.
Okay, and it's the problem that you don't have the correct antenna pattern for your antenna, or can this be avoided pre-launch by calibrating the antenna?
Well, no, we have a very well calibrated antenna pattern, so we know how the gain changes. And we know that the gain is falling off a little bit, but not that much. I mean, not that it would explain these large increases. The other part is the geometry of the occultations for a near polar or for the polar orbiting satellite. The sideways looking occultations take longer. So they are traveling horizontally more, so they see more horizontal gradients. They are also descending slower, so they are collecting more noise. And we don't know what precisely is contributing what to this error budget. We are trying to sort that out, and I'm pretty sure we will do eventually. It's just something that when you're looking more to the side in a row, then there are several contributions that are increasing the uncertainty. That's what I would say.
Yeah,
and we see it even in systematic things, at least for GRASS. For the other ones, we haven't looked yet.
Yeah. So very quick, actually, STAR actually put this reprocessed Cosmic 2 data in FSI and whatever all together. So I think it's good that we have 3 data set, independent process all together, and then we will see what happened. And actually tomorrow we're going to show some of this result. So thank you.
Thank you very much.
Thank you, Christian. All right, thanks everybody. Sorry, we don't have much time for questions if we go the full amount for the talks. Okay, so next up we have Na Chu, who will be giving a talk on China's GNSS